Alright, we're going to go back to this problem right here. We found, in this problem from before, we found the acceleration of this system to be 5 meters per second squared. And because we had a total mass of 6 kilograms and a net force of 30 newtons. Okay, and then we found the forces acting in between the objects. And so between B and C there was a 5 Newton force, and that was the 5 newtons required to accelerate C at 5 meters per second squared. And then between A and B there was a 15 Newton force, and that was 15 newtons required to accelerate B and C together at 5 meters per second squared. And so I want to look a little bit closer at what's going on here. So let's start by drawing a free body diagram for object C. Okay, and I'm going to label these forces in a very specific way so we can think about what's going on here. So object C experiences a push this way from B. So this is a force from B on C. And then we have the weight of C, and so we have the weight from the earth on C. And then pushing up we have the normal force from the earth on C. Working here backwards to B, we have normal force upward from the earth on B. We have downward weight from the earth on B. And then the force from C, there's an interaction here between B and C. And if you're thinking of, if you were block B, you would feel as if C was pushing back on you. You would feel C pushing you. You're in contact with C, block C. You can feel it pushing you backwards. And so you feel this backwards force from C. So this is the force from C on B. And then we have this other force pushing B forward. And this is the force from A on B. And then finally for block A, we have the normal force from the earth on A. We have the weight from the earth on A. Then we have this push this way, the 30 Newton force. And then back this way we have the force from B, block B on A, right? So A is getting pushed that way. It feels block B pushing back against it. Okay, and so I want to highlight some things. So this force here from B on C is tied to this force here from C on B. These forces have the same strength, okay? And these forces are tied together in other ways too. If you increase the push from block B on C, then you're going to feel an increased push from block C on B. If block B stops pushing block C, then block C will stop pushing block B. Okay, so these forces are tied together in the fact that they exist at all. So if you push something, it pushes you back. Okay, so you are pushing down on the chair that you're sitting in, or if you're sitting in a chair, you're pushing down on that chair. And so the chair is pushing up on you. And that relationship exists as a property of forces. Okay, it's just something that happens. When you push on something, it pushes back. And it pushes back with the same amount of strength. Okay, and so this phenomenon is called Newton's third law. Okay. And basically, and you've heard it before probably, even if you've never been in a physics class before, and it goes something like this, okay? For every force, there is an equal force in the opposite direction, okay? So, I mean, think about this. If you take your hand and you push it down on the table, you can't actually push on the table without feeling the table pushing back on your hand. Okay? If you were to if you were to like stub your toe, like you kick something with your toe, you're exerting a force on that object, and you can very clearly feel the force that it applies back on your toe. So those are some examples of Newton's third law. Okay, and so these forces, such as the force from B on C and the force from C on B, are called Newton's third law pairs because they go together. So a great example is with like when if you're weighing yourself on a scale, you push down on the scale and the scale pushes back up on you. That's a Newton's third law pair. Okay, when you knock on the door, you're hitting the door with your hand, the door is hitting your hand back. You can feel that on your knuckles. Okay, when you if you were to hit like a punching bag, the punching bag is going to hit you back, okay, at the exact moment with the same amount of force. Okay, and that's why, I mean, you can feel it when that happens. Okay, and I want to think about some other kind of tricky examples too. Okay, so let's think about this. We have two cars. We have this giant truck and this little smart car, and they're headed straight at each other going really fast, and they're going to collide. Okay, in this collision, which is going to experience a greater force? The truck or the car? Well, according to Newton's third law, they experience equal forces. Okay, the force from the car to the truck will be equal to, but opposite of the force from the truck to the car. Okay, so let's say that the amount of force is 500,000 newtons. Well, the truck's going to experience 500,000 newtons of force. The car's going to experience 500,000 newtons of force. Now, that's kind of counterintuitive because we know that if these two are getting a collision, then the smart car here is going to lose. Okay? Well, if they both experience the same force, why is it that the smart car loses? The answer is the smart car has much less mass. Okay, so when we think back to Newton's laws, if the net force is the same, but the mass is really big versus the mass being really small, in this case we have a small acceleration, or in this case we have a very large acceleration. So while they experience the same amount of force, they experience different accelerations because they have different amounts of mass. Okay? So let's say this is the Earth and this is the Moon. The Moon orbits the Earth because it's trapped in Earth's gravitational field. So there's a force from the Earth on the Moon keeping it in orbit. Okay? Well, does the Moon also pull on the Earth? Do we have evidence that the Moon pulls on the Earth? What kind of evidence do we have that the Moon pulls on the Earth? The evidence that we have is the tides. Okay, the Moon pull on the Earth causes us to have tides. And so high tide and low tide occurs based on the positioning of the Moon relative to the Earth. Okay? So why do you think it is that the Moon also pulls on the Earth? What about another object? So maybe what if something's a little bit smaller than the Moon? Maybe you have like a ball. What if I'm holding a ball above the surface of the Earth? It gets pulled down from the Earth's force on the ball. Does the ball also pull up on the Earth the way that the Moon did? Okay. According to Newton's third law, the answer is yes. Okay. For every force, there's an equal force in the opposite direction. So the Moon gets pulled down by the Earth, and the Moon pulls the Earth upward. This ball gets pulled down by the Earth, and so the ball pulls the Earth upward. Why is it then, when you let go of a ball, The ball is the thing that accelerates downward. Why don't we see the Earth accelerating upward? The answer again comes down to mass. Okay, if the Earth and the ball experience the same force, well, the Earth's mass is ginormous compared to the mass of the ball, and so the ball is going to have some acceleration, and the Earth's acceleration is so small that it's negligible because the Earth's mass is so big. Okay, so the Earth pulling on the Moon and the Moon pulling on the Earth, that's an example of Newton's third law pair. The ball getting pulled down by the Earth, the Earth pulling, or the ball pulling up on the Earth, that's a Newton's third law pair. Okay, the last thing I want to look at is a couple of interactions, just like with the ball sitting on a table. So here we have a scenario where we have a 5 kilogram object pulling, or sitting rather, on a 20 kilogram table, which is sitting on the Earth. And so what I'm going to do is I'm going to do a free body diagram for each of these three objects. Okay, we'll do one for the ball, one for the table, and one for the Earth. Okay, and as we do these, we're going to first focus on their interaction. So I'm going to draw something called the interaction diagram. So we have three objects interacting: the Earth, the table, and the ball. Okay, and so the ball interacts with the Earth through a gravitational force. Okay, the ball has weight. Okay, well, the table also interacts with the Earth in the same way. That table also has weight. The ball is pushing down on the table, and the table is pushing back up on the ball with a normal force. Okay, so notice I draw these arrows pointing both directions because these forces are mutual. And then finally, the table is pushing down on the Earth, and so the Earth is pushing back up again with a normal force. Okay, so let's start with the ball. So when we draw a free body diagram, we don't draw the third law pairs because we're only drawing forces external to the object. We're not drawing the forces the object exerts on something else. But so you can see the ball has two forces. We have the normal force from the table on the ball equal to the ball's weight of 50 newtons. And then we have the downward force from the weight of the ball, of the Earth, from the Earth on the ball, also equal to 50 newtons. Now we get to the table. The table has weight equal to 200 newtons. So this is weight from the table, or from the Earth, sorry, on the table. And then we also have a downward normal force from the ball, because the ball is pushing down on the table. So we have Fn from the ball on the table. This is equal to 50 newtons. This weight was equal to 200 newtons. And then pushing back up, we have the normal force from the Earth on the table, which would normally be 200 newtons, but now the Earth has to push up harder because it's supporting the ball's weight too, and so now this is 250 newtons. Okay, and so finally, let's draw a free body diagram for the Earth. You can see the Earth has 1, 2, 3 interactions, 1 normal force, and 2 forces of weight. So the Earth feels a normal force downward, okay, the third law pair to this force, of 250 newtons. Okay, and this is, instead of being from the Earth on the table, this is from the table on the Earth. And then it has 2 upward forces, one from the ball and one from the table. This is the weight from the table on Earth equal to 250 newtons. And this other one is the weight from the ball on the Earth, also equal to 250, or sorry, this one not equal to 250, this is equal to 50 newtons. And I apologize, the table should be 200 newtons. Okay, so this is the third law pair to this 50 newton force there. And this is the third law pair to this 200 Newton force here.